Almost done. But you need a little more time. Good, good. You are good. Perfect. So, I'm going to start the new lecture. Happy Thursday. Welcome back to probabilistic world and probability and signal analysis. What we're going to talk today, something very, very interesting. Of course, this course is very interesting because it's so practical. Believe me, it may not look practical, maybe look like theory, but in action, you can see the application of that in amazing project and real scenarios. I will tell you some more today. So last class, you learned how to actually play with random variables. However, just discrete random variables, countable. So we said we can actually group some random variables in one family. We talked about family of random variables. Family of random variables, as I think one of your questions in the quiz was about that, is actually they have the same probability mass function, and they are just different in parameters. So those random variables, they all using same probability mass function. But different parameters, like P is one of the parameters that most of the time can be used, or sometimes N and K, for example. Yeah, that's just parameters. In different random variables, we have those parameters. But the general idea, especially probability mass function, is the same. Probability mass function is a function, and function has some parameters, that these parameters can be changed, like N, like K, like P. What else we talked, and what else you learned? I think you also learned about moment. We said sometimes you can define some numerical quantities to summarize how these random variables behave. That's called, we call that moments. We talk about first moment, second moment. First moment was centroid, and second moment was a variance that's showing how these random variables spread or variate around the mean. And that was good. We can see lots of application of that soon. But this expected value or mean is a number, and variance is a number too. So these two numbers that are just constant numbers, they explain general random variables. You have many random variables that are random, not constant, but these two constant numbers can explain them. That's very interesting. Okay, so what else? Oh, we also talk about gambling. We said when you want to do gambling, most of the time you do a trial, and you can be, win or lose. So Bernoulli was very interested to gambling, so he actually work in that, study that a lot, and made formalize these kind of random variables that they can be success or failure. And he studied the distribution of that, or probability mass function of that. Okay, so he said if we do one trial, and you can be success with probability of P and failure with probability of 1 minus P. So probability mass function of X to be success is coming from this. P if X is 1, and 1 minus P if X is 0. So this distribution called Bernoulli distribution, that is the simplest distribution ever, can like formalized. But so many applications can be just modeled with this Bernoulli, like detection, for example. In robotics, we use that a lot. In tracking, also, we use that. Like when you are trying to track objects, for example, or drone, or airplane, or anything, a robot, you can use this probability of detection and probability of not detection, for example, or success and failure, or win and lose. That's called actually Bernoulli distribution. It was very simple. But what we're going to see today, actually this part that I mentioned here, we're going to talk today mostly, even not uniform. Okay, let's clean this up. Yeah, today we're going to build in top of that foundation, last class, and go for another family of random variables. We call that geometric random variable. We want to see what about, instead of just one trial that was for Bernoulli, one trial, we do multiple trial. You know, for example, you want to see this scenario. You have a radar, and this radar try to detect one drone, for example, but send some signals, receive some, but probability of detection is P. Detection. So we call that P of detection, PD, detection. So probability of not detection, 1 minus probability of D. Failure. Okay? So probability of detection is P of D, and probability of not detection is 1 minus P. But sometimes this radar sends signal and not get anything. Try again. We want to see how many times this radar needs to send signal to get a proper detection. So we can consider that as a random variable too. We can say probability of X is K, and K is the number of trial to get first detection. What is this? This is interesting. It's like time. If you do these trials in a certain time slice, you can see, okay, in which time I can get detection. Very interesting. Radar need to do that sometimes. It's not just for radar, for your phone as well. When you are using mobile, sometimes multiple time signal go and come and go to get detection. And that k is a random variable, the number of trial. And that number of trial can be modeled using geometric random variable. You can guess that. OK, imagine I ask you what is the PMF, probability mass function, for this scenario. There is a radar sending signal to the drone to try to detect drone, but I want to see if the, for example, probability of detection is 90%. What is the probability that I get detection in the first time? KB1. What is the probability that I get detection in the first time? When I send signal, I detect it. What is the probability of that? OK, when you get first time, maybe I make it a little more complex. Maybe it's second. OK, I want to see what is the probability of x is equal to 2. So if I said it's the second time I get detection, so it means in the first time you didn't get detection. You get 1 minus p, and second time you got p. The first time you didn't get detection, so with this probability, and for the second one you got the probability of p. This is going to be like that. If I say what is the probability of get detection in a third time, so probability of x is equal to 3. It means first time you sent, you didn't get detection. What is the probability of that? 1 minus p. Second time you tried, again didn't get detection, another 1 minus p. Third time you got detection, p. This is for, and you can guess for k, gonna be p, 1 minus p over power k minus 1. That's why this is called geometric, because it's get geometric series. We're going to see that soon. So I just wanted to give you a general idea that how we can play with these families of random variables and how many applications we can find about that, like in this example. OK. Now let's make this scenario that we have one drone, make it 3 drones. What's going to happen in that case? I clean this up. Make it more complex, because in real scenarios, most of the time, we have like some challenges that happen. Like instead of having just one, you have 4 drones. And you want to see what is the probability of getting all of them detected, or 3 of them detected, or 1 of them detected, or none of them not detected. That's another question. So we want to find, in this case, what is probability of, we have, for example, 4. We know that we have 4, for example, from somewhere. But we want to see what is probability of detecting 2 from 4. Detection of 2 from 4. So what is this probability? This is another family. They are all around Bernoulli. We are just playing with Bernoulli in different way. In Bernoulli, we did one trial. In these two cases, geometric or this one that is called binomial, we are doing multiple trial. That's the difference. The rest are the same. The P is probability of detection. 1 minus P is probability of not detection. So in this case, we need to, again, play with that. We want to see what is the detection of 2 from 4. So detection 2 from 4, it means 2 detection and 4 minus 2 not detection. Is that right? But we need one coefficient that we learned in last class and was combination of that. That was 2 from 4. So this is another family of random variables that we call it binomial. Because it's binomial. Do you remember about this combination? Combination was actually selecting like 2 from 4, but order is not matters. So that's coming from combinational formula. That is 4, this is going to be 4 factorial, 2 factorial, 4 minus 2 factorial. Okay, so we're going to see that today. So this is another application of probability. This was for tracking and detection, but there is so much more applications that can be used in this pattern. And that's why we call them the family of random variables. So these two families, geometric and binomial, are two families that we're going to talk today. OK, let's get started. First, we start with one quiz. Try to do this. It's not quiz, actually. It's just iClicker. I just want to give you idea. So we have, let I define that. Go to quiz and do start and do pool. Start the pool. Okay, so, try to do that. We are saying a mobile robot. We have a robot send a status message to the base. This can happen a lot. For example, in some scenarios, like firefighter robot, when you have a robot that is communicating with the center, and this is, for example, firefighter robot. There is a fire, wildfire, for example, in the forest, and you send lots of robots to go and, extinguish this fire. And sometimes it's one, sometimes multiple, and these multiple robots need to communicate with the server. Okay, they need to help each other because the fire is dynamic, fire is moving, and this need to adjust their position to optimize this. This is very complex problem because everything is dynamic. They are all moving. Fire moving, robots need to adjust. They find the best place. We have wind factor here, wind effect. When, for example, wind comes from one direction, robots need to understand that fire, for example, going to that way. So they need to adjust they don't need to go behind the wind. They need to go ahead of that. That's a very complex problem. But in this class, you can learn how you can solve it. What do you mean by solve it? It means you find the best position for the robots to maximize utility. What is utility here? Utility here is, for example, to finish the fire as soon as possible without expanding that, or and don't make trouble later, you know. Yeah. So to do that, they need to find the best place that they go. And yeah, anyway, this is one of these examples. So waiting time, we are asking, we have a mobile robot that sent its position or a status message to the base or center. And sometimes, because it's the environment that is not trustable, sometimes this information is not receiving properly. So we have some attempts that is success and some attempts that is fails. But this happened independently. So that's the important part. Failure or success happen independently. So the probability of success is P. We know that. And the robot keeps trying multiple times. And we want to see what is, and define X as a random variable that is a waiting time. OK? So I ask you, which description is the best match for X? X is a waiting time. So the first is, OK, so let's see what is your response for that. Yeah, mostly they consider C, and this is correct, yeah. So yeah. So yeah, as you can see, oh, here. Yeah, C is the correct answer. So because the number of attempts until the first success, because we do, if first happened, we don't need to send again. So that's why this is the best answer. But that's the correct answer. Let's take that back. My screen. OK. So the C is the correct answer, of course. So I just wanted to give you idea what's we going to deal today. OK, done. And OK. Any question about that? OK, so anytime you are dealing with time, you need to go with this distribution. For example, you want to see what is probability to stay in a queue, for example. This time, you need to use geometric distribution. OK, what is geometric distribution? Geometric distribution is actually questioning how many trials you need to do until first success. So as I explained in the first slide, because one of them is success, the first success, the rest are failure. If this, sometimes we call this X is K, the number of how many trials, sometimes we consider K or X, doesn't matter. Here we consider X, but it can be K too. Anyway, so one success and X minus one failure. So that's why it's coming from that. Why it's like that? Because it still is Bernoulli. But we tried multiple. This is still Bernoulli. Why is Bernoulli? Because we just have failure and success. But we try multiple times. OK? That's a probability mass function. Why we call that geometric? Because any idea? I think I already mentioned, kind of. Why this is geometric? Why we call that geometric? Why we didn't call it something else? Anybody remember geometric series? You had that in geometric series was like something like, for example, P maybe series doesn't have plus. And p power, for example, 2, p power 3, p power 4, p power, k, for example. This series is geometry because it's multiplying by something, okay? So here we also have the same probability of first success, x is 1, is p. Probability of second success is p minus 1. Probability of third success is p minus 1 square. Probability of fourth success, p minus 1, 3, and go forth. So if we factorize this p out, and the rest is geometric. That's why this is a geometric. It's called geometric random variable. Okay, so I just wanted to let you, okay, why we call that. So that's geometric, because it's multiplying by this p minus 1 every time. So he's make a series. But a geometric series are, even though it's going to infinity, when we add them up, we can find the final solution for them most of the time. Like, for example, if you add, for example, p plus, if you add this together, like in a form of like pk, k from 1 to infinity is like equal to 1 minus p, something like that. You know these things. You also can get differentiation from this. You can say k, p, k minus 1, k is 1 to infinity is equal to 1 minus p square. So, and you can get another differentiation to get for example, that k minus, k minus 1, sorry, this is k minus 1. K minus 1. Okay. And you can go with more differentiation. When I'm talking about differentiation, it means I get differentiation from this side and this side, respect to p. Respect to p, we're going to get this one differentiation. Second differentiation going to be also more complex. But we need the first differentiation soon later in next slide. Okay. Any question about this? This series is very well-known series. I'm talking about geometric series. Very well-known series. You had that a lot in your classes before. Let's clean this up. So, okay, something very interesting in this geometric series happening that is called memoryless. First of all, it's model waiting time. We already know. But another thing that's happening is memoryless. This memoryless property is important for us. So what memoryless means? Any idea what memoryless means? It means yes. We don't, yes, exactly. We don't need to memorize before. Whatever happened before, we don't care. If we repeat it 10 times and we failed and failed and failed and failed, if we want to try again now, probability of success still is p. That means it's memoryless. Some phenomena are not memoryless. They are dependent before. Like, for example, your success in this class is not memoryless. For example, you want to get good grade, For final, you need to have good grade in midterm, good grade in second midterms, and then final. Passing, for example, in this class depend on the past actions that you did. That's not a memoryless. Memoryless is an action that it's not related to before. You know, the probability of being success is just related to right now. This kind of actions called memoryless. Sometimes some actions are just related to one step before. We call them Markov process. If she's just related to one step before, not many times before, that's called Markov models, that we're going to see that in this class soon. Markov models can be used for robotics a lot because the position of the robot is just related to one step before, and where you are now, you can estimate what is the future. So that kind of process is Markov. Why one step before? Because one step before, and now you can calculate your speed and velocity. So you say, okay, I was there, and I'm here after 1 second. So my velocity is this. So I'm going to be there in 1 second later. You are predicting future based off one step past. That's also very simple mathematical way. We call it Markov. Markov is a very amazing mathematician, Russian mathematician that did that for his first time. So this is not Markov. This is even memoryless, even not related to one step before. It's just related to now. If you want to get success, don't look at the past. Just start right now. Anytime you start right now, you can be success. Okay, that's a good expression for that. Okay, so memoryless means that. Mathematically, if you want to mention what memoryless means, we can say probability of a random variable x bigger than s plus t, and given x bigger than s is equal to probability of x given than t. This is mathematically explain whatever I said. But don't worry if you don't understand that. We're going to talk about that later. So in general, we are saying if probability of x, but if it's x bigger than s, it's not related to s anymore. It's just related to t. T is right now. T is the moment. Okay, good. That's a memoryless. Memoryless is a good characteristic of geometric random variables. Some random variables are like that. Good, that's good. Each trial is independent. So that's independency coming from Bernoulli. So two things coming from Bernoulli in this. First, independency, and also the distribution. Still, we have success and failure. P and 1 minus P is the same. But we repeat it many times. We repeat that many times. OK, that's good. Example, we did lots of examples, but this is another example. Number of tests until the first defective circuit is found. For example, in a factory, you want to see which circuit that you are manufacturing is defective. You can use this distribution for that. For networking, you also can use that when you are transmitting data in the network. We want to see like you are studying the first success. Like for mobile can be used for that robotic systems that you are trying to communicate with your server or your base. This can happen too. You want to see how many times you need to try to get success. Okay. Another example. This example we already talked about that in your iClicker, but we're going to explain this more here. So we have the same scenario. We have a robot that communicating with the base. But in this case, we know the probability of success is 0.70%, and probability of failure is 1 minus p, that is 30%. Okay? So we know this one too. And x is the number of transmission until the first success happen. So this is geometric. This is probability mass function. And what we ask, what is the probability to get success at the first time? Probability of getting success at the first time is just p, 0.7. Probability of getting success at the second time is p, 1 minus p, is 30%, and 70% is 21. And probability of x is third success is p, 1 minus p squared. So you can compute that. Here is a better, cleaner version. And go for it. You can see, we can find the probability of getting success after a fourth trial. Okay. That was actually geometric. I think we are done with geometric. Let's go to another. But because before going there, if you have any idea, any questions, anything, not clear, let me know, okay? Any question? No? Okay. Oh, we didn't compute mean and variance, of course, because we know mean and variance, or moments, how we can compute mean and variance for geometric. For geometric random variables, we also can find mean and variance. So this is, we have probability mass function. One of the way to compute mean and variance is to use probability mass function. We computed that a couple of times last class, but we can do that here as well. If you remember last class, we said probability expected value of x is equal to actually average or weighted sum. Weighted sum is like that. K for all k, k and probability mass function, P of x is equal to k. So because it's like that, you need to find this summation k, 1 minus p, k minus 1, p. Because p is not related to k, you can bring that out. And the rest is k, 1 minus p, k minus 1. If you remember, in the last slide, I computed that. That's a geometric series, but like a differentiation one. But I'm going to do that here again, too, if you didn't get that part. So we know that sum of xr in general is equal to 1 minus 1 oh, yeah. K from yes, if we do r from 1 to infinity is 1 minus r. Okay, so we know that. And if we do differentiation from this, I mean d of this and d of k, d of r, sigma infinity r is 1 to this is equal to differentiation of this side, 1 over 1 minus r. So this is going to be 1 minus r squared. And this is going to be r x. Oh, I think I messed up. This is r. Actually, if this is x, this is going to be 1 minus x. Am I right? Yes. Okay, yes, that's right. And this is 1 minus x. Okay, it's 1 minus x. Okay, and this is going to be r minus 1. Okay, because I mix r with k, and that's a problem. And r from 1 to infinity. Okay, so we want this formula. And this is exactly this. But instead of x, here we have 1 minus p, for example. So E of x gonna be we have 1p, and the result of this is going to be 1 minus, and what is p here? 1 minus p is going to be p squared. So it's going to be 1 minus p. Okay, so that's computation is not that important. You just need to use geometric series to find that. But if you do that and do differentiation, you can get that formula. The result of that formula coming from this, like x is 1 minus p in that. So if you put that in that formula, 1 minus p, 1 minus 1 minus p, that is going to be plus p. 1 and 1 going to go cancel out, and p going to stay there, p squared. And p squared with p going to again cancel out, and 1 over p. Okay? Okay, I'm not going to go for variance. I'm just going to give you the formula, but you can compute that as well, same way. So this is the mean. I'm just going to clean this up. Any question before this get cleaned? Okay. But in your lecture notes, I wrote this. You can check that if you have problem. But I'm not going to ask that. It's just for how prove it, but it's not that important in my point. Okay? So the variance is going to be the same way, because we know variance of random variable x is actually expected value of x squared plus expected value of x square, all of it. So this is equal to this. Last class we proved that. So you can use the same idea, and when you do the math, you're going to get this as a result. Okay? So this is something that we just need to know. The important part is not computing this formula to get this idea. The engineering part of that is that when we increase the p, what happened to variance or expected value? So when we increase the p, like probability of success get higher, expected value get lower. And when p gets smaller, like probability of success gets smaller, so you have large delay. You have large delay. And highest variance. So that's something that we can get from this formula, because they are reverse compared to p. So they are reverse of that. When p increase, expected value decrease. And variance the same, because it's a square. So this if you do the limit, it's still going to act similar, you know. When p gets smaller, you know, the variance gets higher. Okay, something like that. Okay, so that's a general idea about mean and variance for geometric random variable. But geometric random variable, the important part of that is the time for success. When you want to find the number of trials or the time to get the first success. Okay, that's finished. Let's go to binomial.
I have a question.
Yes, yes. Yes, yes. Oh.
Variance from k squared, is that just k squared or is that the whole thing squared?
This one?
No, on the blue.
Oh, this formula?
Yeah. Where it says, is that a k or?
Oh, this formula. This is expected value of x squared. Look, like instead of having x, we have x squared. And this is expected value squared. So this is for just this part. Just this part squared.
That's an x?
No.
Like the variables you're using, are they both x's? You know, e to the x squared, and then it's plus e to the x whole squared. They're both x's.
No, is like, for example, expected value is 1 over p. This is going to be 1 over p squared. Yeah? But computing that part is complex. You need to, I can do that a little bit to show you how this is happening. So for that part, if you want to compute this one, you need to find this one. So yeah, p of variance of x squared is 2 minus p squared. This is how we you need to compute that. Variance of sorry, this is p e, sorry, it's mixed up. And e of x all square is 1 over p squared. So I just specify these two. If you put these two together and do this plus, is it? Oh, it's minus, not plus. This is minus. If we eliminate this from this, you're going to get that. You can see the complete answer in lecture note as well. Okay, any more question about geometric random variable? Let's go to binomial. We need to finish this as well today. So binomial random variable, again, we are doing repeating Bernoulli trial. Bernoulli trial was success and failure, and we are repeating that. But here we want to see, like that example that I said, multiple drone. We have, for example, we have n drone. We want to see what is the probability that we detect 2 from n. That distribution is binomial. We are not dealing with time anymore. We are with probability of detection, same. So exactly similar what we were doing in binomial. In binomial, we wanted to see probability of detection or not detection or failure or success. But in Bernoulli, it was just 1. In binomial is n. Okay? That's the difference between binomial and Bernoulli. Binomial is actually repeating n time Bernoulli trial. That's how but is independent, remember? Independency is the big issue. Again, the rate of success or probability of success is P, and failure is 1 minus P. And probability mass function going to be probability of, like, for example, detecting K time from N target is because we get success K time and get failure N minus K time coming from this formula. And because it has a repetition, we need to use the factor, the parameter or coefficient that is combination. Combination of K from N. Okay, we also explained at the beginning of the class how we deal with this. So that's a PMF, or probability mass function. Still we are dealing with discrete random variables. Okay, that's a cleaner version for that. So again, what that means, it means we are doing Bernoulli, a random variable, but we repeat it n times. We repeat Bernoulli n times. Like, for example, you are you have a coin, and you drop the coin multiple times. Every time it can be, for example, head or tail. For example, head is success, tail is failure. So in that case, is probability is just 1/2 because it's equal if it's proper coin. But in general, it can be P. Probability of success can be P, and probability of failure can be 1 minus P. But you are repeating that many times. And what is the question? Question is that what is the probability that you get 2 times success, 3 times success from 10, for example, 10 times. So this is coming from a binomial distribution. So K times success, N minus K time failure. Any question about this formula, how I wrote this? For example, why I put N minus K for 1 minus P? Because failure happening N minus K time. And what is the probability of failure? 1 minus P. Easy. But we need to, because we repeat that many times, we need to consider this coefficient for that. So that's called binomial coefficient. And binomial coefficient is a combination. And we had combination last chapter, chapter 2 of the book. We are in chapter 3 right now. We talk about permutation and combination, you know. Combination, actually, order is not matters. Order is not matters. That's the important part. Okay, so that's binomial. Let's see application. Oh, okay, if you want to draw the diagram for that, so we have here, in binomial, we have 2 parameters. One parameter is P. Another parameter is N. N is also parameter because we want to see what is the number of trials. N is the number of trials, not number of success. Number of success is random variable. This is number of trial. Number of trial. So we have 2 parameters. One P, that is probability of success, and N is number of trial. In this diagram that you can see it's like a bell shape. The reason that is bell shape because of this probability that is 0.5. So this shape is a binomial probability mass function. If the n is 10, as you can see, n can be 0, 1, 2 to 10. And k is the random variable. X is equal to k. K is a number of success. For example, showing number of success, this is actually for coin, I think, because the probability is half. It's for coin. Imagine you are 10 times dropping the coin, and you want to see how many times come a tail or a head. For head is success. 0 is probability 0. 1 time success, 1 time head, probability is so low. 2 times probability is 0.5. 3 times is this much. And highest probability is when you get actually 5 times success. When you drop 10 times, probability of being 5 success is highest. Why? Because it's a coin. It's a normal coin, and probability is half-half. OK, I just wanted to show this in graphical way as well. So in graphical way, when you have discrete time, you can see like that, like a chart, a bar chart. But in continuous time, you can see that as a continuous curve. Later on, we can see in a continuous way as well. That is a normal distribution, actually. OK, what characteristic we can say? OK, Bernoulli is a special case of binomial. Why? Because if n is 1, it becomes a Bernoulli. And we have parameters. We have n, number of trial. We have p, probability of success. And k is the number of success. That is my random variable or random variable. K is the random variable that we are trying. And k can be 1, can be 0, can be 1, and here can be even 10. So probability of 10 times come head is so low. But probability of 9 times is this much. But probability of 5 times get head is highest. I just want to explain different ways, to help you understand this. Yeah. But I'm going to tell you guys, this binomial is the hardest things that we're going to see in this class. In terms of formula and complexity and combination, or, that's the hardest part. Don't scare if it's lots of formula and factorial. This is so you're not going to see that more. That's the hardest part. Okay. So mean and variance, because binomial is actually n time Bernoulli, we just need to add them together. So the x is actually add of n times, so the expected value is also add together. So expected value for Bernoulli was p, and for binomial is np. And variance, same too. Variance is add of variance. We are repeating independent binomial n times. So for Bernoulli, the variance was p, 1 minus p. Here going to be n multiply p multiply 1 minus p. That's it. For just example, this is very simple example. We are flipping a fair coin, same things. The probability is half. Probability of tail and head are equal. We are trying 5 times. We want to see what is the probability. 2 times get head. So combination 2 from 5, p power 2, 1 minus p power 3. That's it. This also can be for bit error. When you are doing data transfer, same things. We are trying to send 10 bits. Probability is a 90% success, 1% error. We want to see what is the probability that a 2-bit get error. So combination 2 from 10, probability of a failure is 0.01. 1 minus p is this. Add them together. Multiply them together. That's it. This has lots of applications that we saw a lot in digital communication, reliability, computer networks, and security, and tracking, and much more. We can see them later as well. OK, guys. See you next week. And we're going to have one assignment tonight. OK, have a good day.
I hate his back.